record. All right, it is now recording. Okay, so as I said, we're going to go through the material. We had previously gotten to section 4 when my internet went unstable, and hopefully we'll get back to there very quickly and then continue on with the remaining material. So we've been using a very simple kind of object, a set of up to 1,000 dice, each one having either a 0 or 1 on them, because it's got 6 outcomes, and in any Newtonian phase space, each particle also has 6 objects. That is the x position, y position, z position, x velocity, or actually momentum, y momentum, and z momentum. So we're mimicking the type of material going on in Newtonian mechanics. And but by forcing them to be 0 and 1, I can let zeros be on the left side of an object and 1s be on the right side, so that if we take a look at this kind, this is done in 3 dimensions instead of 2 dimensions. But these are the start of the particles going down for the first 100 steps. This section is plotted over here. So as we continue to move our dice around, it gets more and more the same. And as you can see, these dice are being either on the left side or on the right side. And so I hope that these very simple probability models we've been using, which are very similar to the adiabatic free expansion of a gas, gave you some insight into how it actually behaves in a real ideal gas. And many real gases actually, over many regions of temperature and pressure, do follow the ideal gas law. All right, so there's lots of statistical things that we could be talking about, but we're primarily going to be trying to understand the ways and basic techniques and concepts of statistical mechanics. And I will show some definitions of temperature and pressure and entropy as we move on. So we've talked about an isolated physical system. Can somebody describe what an isolated system is?
Something sealed in a box.
Yes, well, what it means is no energy, no mass can go through the boundary. So all of the energy must stay within the boundary of the system, and no energy or mass from outside the system can come inside the system. So it is just everything in the box, but it means nothing can go through the boundary in either direction. Okay, so we're going to be dealing with quasi-particle systems, and we're going to be talking about microstates and macrostates. And a microstate defines the values of all possible microscopic variables. In Newtonian mechanics, that's phase space. Every particle has, as I said, 6 items on it, and the phase space is 6n dimensional space. So if you have n particles, then you have a 6n phase space, and the system is a single point in that phase space. I've done that picture a number of times before with simple systems moving around where you have 3 particles bouncing across with each other, and then I show how you can show it as one particle operating in 3 dimensions. Okay, so we're not going to deal with quantum mechanical systems, but you can add this into thermodynamics and statistical descriptions using the wave function. And there's a lot of more information about microstates that you could use that are way more than you're ever going to want to use for, but just want you to be aware that this is a very limited approach that we're doing right now. Okay, so since I can't draw pictures in more than 3 dimensions, I'm going to use very simple systems. I'm going to use a lattice phase space rather than a continuous one. That means that the delta x's are going to be fixed and the delta p's are going to be fixed. So the phase space that I'm talking about is actually a list of points, all the red points that are shown here. And the number of microstates in a typical system is huge. If you think about a box with molecules bouncing around inside, the velocities of every particle could be different. The angle at which they're bouncing off something else could be different. And so microstates are just tremendously huge numbers of systems and much more detail than we usually consider about and don't need to know anything about. A macrostate, on the other hand, is by specifying some value of every macroscopic variable in a macroscopic measurement, not a microscopic measurement. So typically, if we're talking about the kinetic energy of the gas, then the average kinetic energy of the gas is what we call the temperature. At least I'll talk about it in probabilistic or statistical mechanics, but that's the way in which the idea is. So we've talked about there's a tremendous number of microstates that correspond to any particular macrostate. And that number of microstates that correspond to the macrostate is called the density of states. And it's usually written with a large omega, and there can be many kinds and this gives you the macroscopic measurements. So in this particular case, the density of states would be by picking an energy, a volume, probably a pressure, whatever else you need to use. So in our system, they're of course discrete, and so physicists usually treat these as a continuous function because the numbers are so large to deal with, and doing actual sums instead of integrals is just not very useful, and give almost exactly the same results anyway. So as long as the allowed values are all sufficiently close together, the total number of macro states in any given interval will be huge, and you can use a continuous approximation. All right. So typically you take a look at the number of microstates per volume in phase space, and that's the number density. So as an example, if you had a single free particle in 3 dimensions, the microstates are just a 6-dimensional phase space. That is the position x, y, z, and the momentum in x, y, z vector space. The energy is the magnitude of the momentum squared divided by twice the mass. Everybody knows why that's true, right?
No.
Okay. The momentum is mass times velocity. So mass times velocity dotted with mass times velocity gives you mass squared times velocity with the magnitude of the velocity. And now you divide that by 2m, and that gives you mv squared over 2, and where the v is the magnitude of the velocity, the speed. So the kinetic energy is mass times speed squared divided by 2. So we just reproduced that, right? Fred? Okay, good. Okay, so each version of, so we can consider this to be in a 3-dimensional momentum space, which is portion of the phase space. And this energy is, we know, conserved, so it's a constant. So if we have a 3-dimensional momentum space, and we have an equation here for a constant is the mass times the velocity squared, or speed squared. So this provides a 2-dimensional surface, and that surface is a sphere because it's got a constant radius. So the yeah, as I said, a sphere of radius magnitude of p about 0, 0, 0 would all have exactly the same energy. So the density of space is proportional to the area of that volume, and the area, everybody knows, is 4 pi r squared. So r is the magnitude of the momentum. So the density of macrostates, or density of microstates, I should say, is proportional to the magnitude of the momentum, is proportional to the energy. I'm not going to worry about the fact that we've been dealing with density with discrete systems. Now, if you have a collection of n such particles, the momentum space, as opposed to the phase space, is 3n dimensional. If you go for the kinetic energy, you know again that it's the sum over all the momenta, but in momentum space, all of those momenta are a single vector. So you have, again, exactly the same result, that the density, the number density is proportional to the magnitude of the sum of all the momentums in a, it is a sphere. The energy is a sphere in 3n momentum, which means that the surface is 3n minus 1 dimensional surface. And so we can write the same kind of a result, except we now, instead of having 3 minus 1, we might have 3n minus 1, and we have the microstate density is proportional to the energy over 3, assuming all of the particles have, well, yeah, it's the surface of a sphere. So if you know the energy, you can work it back to be the energy divided by 3n minus 1 divided by 2. Okay, so hopefully everybody understood that the vector in momentum space, 3n dimension, is a list of all of the particle momenta. So it's 1, 2, it's all of these things listed in a long vector. And we just went through the derivation. I'm not going to do it again. One of the postulates that I'm going to use, and which is actually based on what Boltzmann did, is the postulate of equal a priori probabilities. And this is the assumption that every microstate has the same probability in its current macrostate. And this was the way Boltzmann used in order to develop his entropy formula. So this can sometimes be justified. In practice, it works very well for many cases, but there are some theoretical problems, arguments for it. However, it is not always true, and we will eventually get to Joshua Gibbs and deal with unequal probabilities. But for now, we're going to deal with equal probabilities. Everybody up with me? Okay. So to use a slight way of thinking about this, an isolated system that satisfies the postulate of equal probabilities is said to be in equilibrium. So that was the reason that Boltzmann actually wanted to do it, because his H theorem showed that eventually temperatures between two different systems will equilibrate. And in order to get there, he needed to postulate these equal probabilities. In some previous material that I'd used, I said there was a probability of a system being in a particular microstate. I never defined what that meant. So we're going to, in any particular microstate, obviously there's no probability about it. It's in whatever the microstate is. However, you can define probabilities in this context, and you realize that there are many different changing systems. And because you don't know which one it is, they're all different. We just assume that as they change over time, they're equal. We can think about the probability of a system being in a microstate as the fraction of time it spends in that state, if we're using the idea of the system evolving over time. Prado, out. Prado, come on. You got to be quiet. Sorry. Okay. Averages using this definition of probability are called time averages. And this was the definition that Boltzmann used in his H theorem. It turns out to have problems, so we're going to look at it in a slightly different way, the one that people use more recently. And these are where we consider an average over an ensemble. And I'll talk about an ensemble. So in practice at time, we have only one system in one microstate. However, I don't know which one it is. And we can do the probability of the system being in a microstate as the fraction of an imaginary collection of systems that are in the microstate. So a statistical ensemble, which is what we're talking about, is a collection of all the possible microstates that correspond to that particular macrostate. And that ensemble, you can take the average over that, and that defines a probability, and we call those ensemble averages rather than time averages. Now, there is another theory called ergodic. I think that's what I'm going to do next. Yes, okay. And the question is, are the two equivalent? And the time averages versus the ensemble averages. And it is emphatically sometimes. For some systems they do, other systems they don't. So I'm going to assume that all the systems we're working with, and because we're doing things quasi-statically, it will be true. The system time averages and ensemble averages are equal. Somebody, you've got somebody calling, please mute your Zoom. Okay. Ergodic is an interesting word. It's Greek for work and path. And if you remember our empirical thermodynamic lectures, work and path were very important factors in terms of understanding how thermodynamics works. So we're trying to make a better description, and we're going to take the definition about the postulate of equal a priori probabilities as being in equilibrium. So an isolated system in equilibrium, if the probability distribution of its microstates do not change with time. And since they don't change with time, obviously the ergodic process will be the same. If you take the average over time or you take the average over the ensemble, they'll give you the same result. Okay, so let's move on to the Maxwell-Boltzmann distribution. And there's only so much you can really say about isolated systems. As I've said many times in various lectures, real systems are almost never isolated. They're embedded in some sort of environment, and the interaction with the environment is usually so complex. So there's a trick that is used in thermodynamics, and that is simply to deal with everything that is not in the system to be huge by comparison, and therefore we call the environment a heat bath. That means that the only thing, all of the environment we assume are usually in equilibrium, and whatever temperature they have there, they're so large that they can continually leak heat into the system A. And we'll usually be dealing with systems that are in a heat bath as opposed to isolated systems, because isolated systems just really don't exist. Okay, so a couple of examples. You have part A of a gas is contained in a box. Part B in the box itself is the whole room containing the box. So the assumption is that the volume of the gas in the box is very small compared to the volume of the box itself, and the temperature, because it is so, the room is so large compared to the box, you can ignore all the transportation back and forth across the box, and it just goes from the heat bath part B into the box part A. Another example is A is a test tube with chemicals in it. Part B is a water bath, again, assuming to be a very large bath in comparison to the test tube. A third is all the air in a room. Part A is the carbon dioxide molecules in the air, and part B is everything else, nitrogen, oxygen, etc. So you can always decompose the energy of a system into its total energy equal to the part A plus part B plus the energy of the interaction. And what I've been arguing by using a heat bath is that the intersection, the region that is the two interacting with each other, are essentially zero. And essentially is the key word. So we will assume that the interaction between the two is small enough that we can ignore it. And that is a postulate that we need to work with. Now, obviously, if it were really zero, the two subsystems would not interact at all. And you would just have two independent, isolated systems. Obviously, this is not accurate. So what we want to try and deal with is something that is weakly coupled. But for the statistics that we're going to be dealing with, we're basically going to say that the density of microstates of A and B, the total, is just the product of the two. And that's this. This is close enough we can ignore all of the interactions. So having subsystems that are weakly coupled requires another assumption. The previous assumption was that they were being weakly coupled through the energy function. And the other assumption that I need to make is that the log of the density of the energy of system B is linear in the energy. Now, obviously, you can always take any function and use the first two terms in the linear approximation, but those are only going to be accurate for a small region of energies. However, because we're dealing with things being quasi-static, the energy is essentially almost always static, so the linear approximation is actually pretty good. Okay, so I'll skip the energy approximation examples. So what have I been trying to understand? The total energy of a system is E sub T. We want to describe the probability of system A being in one particular microstate in energy A. So we have our assumptions. The complete system is A union B minus A intersection B. This is just normal set theory. And it describes all possible microstates in E sub T. The postulate of equal a priori probability of every microstate in T simply says that every microstate is equally probable. And some of the T microstates involve A being in a desired microstate. That energy is E sub A. And the other microstates in T do not involve in that particular microstate. So the probability of A being in a desired microstate whose energy is E sub A equals the fraction of microstates of the whole system, that is the ensemble average for T, for which A is in that particular energy state. That's simply a definition. So if you have a total number of microstates in a system with macrostate energy, let's say the energy is 15, and we assume that the system A has 3 energy macrostates, so we call them E sub A 1, 2, and 3. And further, there's one microstate E sub A1 that is, there's E sub A1, E sub A2, E sub A3. In order to compute the probability of macrostate E sub A3, we know there are 3 microstates for this particular macrostate, and it has a total of 15 microstates. So the collection of E sub A3, which we've said has 3 microstates associated with it out of the 15, means that the probability is 0.2 or 20%. Assume that's all fairly straightforward. Okay, so we've used this linearity and of the total temperature being E sub B plus E sub A. So we can turn it around, say E sub B is E sub T minus E sub A. That's just very basic algebra. Our second assumption is the independence, that is the weak coupling in the systems, and therefore that we can deal with them as the product, which means if we take logarithms of everything here, we will have the log of EB plus the log of EA, which is approximately the log of E sub B, which is equal to log of E sub T minus E sub A. So we've changed our definition of E sub T to E sub B as E sub T minus E sub A, just again using our linearity. The third assumption is that because these are logs, the energy is the log of that, then the density of microstates is the exponential of that linear approximation. And we can finally get back to what we were trying to get to, which is that the probability of E sub A is proportional, because we're dropping out the constant alpha, is just the exponential of beta times the energy, the macrostate energy E sub A. And the way in which normally temperature is actually defined, not the empirical one that we talked about previously, although that gives you the same result. If you take the logarithm of the density of states and take the derivative with respect to the energy, you're going to wind up, obviously, the log of this is going to get rid of the exponential. You're going to have alpha plus beta E sub B, so, or E sub A in this case. And so when you take the derivative of that, you're just going to get the beta. And that is the definition of temperature. Beta is, or inverse temperature, I should say, 1 over KB times the temperature in kelvins is that constant in the linearity that we've assumed. As you are obviously we've been saying, this is temperature in degrees Kelvin. K sub B is Boltzmann's constant, a really small number. But beta is called the inverse temperature, as I said, and the probability can be written in terms of the energy divided by Boltzmann constant times the temperature. I'm still missing the proportionality of constant alpha that I threw away, but it's easily found because you can simply sum all the probabilities that there are in the microstates, and they have to add to 1. So the normalization constant is usually defined by what's called the partition function. And the partition function is just the sum over all possible microstates. That is the sum over the ensemble of microstates for energy E sub A divided by Boltzmann constant times temperature. And it is also an interesting function on its own right, and an important function, but we're not going to deal with it. If you're interested, you can continue looking at statistical thermodynamics and statistical mechanics, and you'll find that the partition function is very useful for computing many things as we go along. So now we have the probability of the macro state in energy E sub A. I'm sorry, each of the microstate, the probability of each microstate is equal, and it is equal to the macroscopic energy E sub A divided by the Boltzmann constant times the macroscopic temperature in Kelvin T divided by the partition function. So each of the microstates that have energy E sub A, which is a macro variable, and temperature is a macro variable. We're assuming we're quasi-static, so this is essentially constant. So this gives you the probability for all of the equivalent microstates. And this is one of the major results we've been trying to get to. This is called the Maxwell-Boltzmann distribution. And we're going to go a little beyond that, but this is the way in which Maxwell and Boltzmann actually thought about doing statistical mechanics. Is everybody understanding how, given two macroscopic measurements, the energy of the system A, the temperature of A, we can calculate the equivalent probabilities, the equal probabilities for every microstate that there can be. Is that all clear? Anybody need any questions? Okay. So Boltzmann used this postulate of equal a priori probability in his H theorem, and he loved his H theorem so much that he had it on his headstone, and he used the H theorem, but we call it entropy, and his constant K, I don't know if you can see this in here, this is S equals K log W, which was the result of his H theorem, or one of the results of his H theorem. So Boltzmann considered, now we're moving on from Maxwell to Boltzmann. Boltzmann considered what happened during collision between two particles. And he assumed that these were basically two hard spheres, and the energy transferred between the particles on initial conditions, angle of collision, etc. When he made these assumptions, he also called the Stolze-Glansatz. I don't know German very well, so I apologize. The molecular chaos assumption. And this assumption was essentially that equal probability assumption. And we'll talk more about this in a article that Boltzmann actually wrote 6 years before Boltzmann did, and produced the same results that Boltzmann did. Unfortunately, he didn't do it logically consistent. He made a couple of assertions which needed to actually be postulates, but we'll talk about that later. Okay, so the assumptions that Boltzmann used in his molecular chaos assumption was that independent chosen kinetic energies from the distribution, so they're all independent, the independent velocity directions. They can go, obviously what we're talking about here is spherical symmetry, using the key results of symmetry that we always talk about, and independent of starting points. Under these assumptions, and given the mechanics of energy transfer, the energies of particles after collision will contain a new random distribution that can be computed. And under the assumptions that he made, they basically are assumed to be uncorrelated collisions, and hence the process of collisions doesn't change over time. Slowly, the assumption here is that they're equilibrating in a time frame very short compared to the time changes that we're talking about, able to measure things macroscopically, such as energy or temperature. And from the continual process of collisions, the quantity that he called, well, he initially called it E for entropy, but one of his critics, Burberry, wrote the symbol H, and subsequently Boltzmann referred to it to his H theorem, even though he had used E originally. And both E and H are, in modern terms, S, the entropy. So previously, I've assumed that a single macroscopic variable energy. We could add a more general case. So suppose we have two macroscopic variables, energy and volume. We can consider a balloon filled with helium so it can stretch or contract, exchanging volume as well as energy with the surrounding. The density of states will now be linear in the two variables, E sub, so alpha plus beta E sub B plus gamma B sub B. And we use exactly the same logic that we used before, and the probability of all the equivalent microstates is exponential of beta plus gamma B sub B. And the partition function normalizing is just the sum over all the energies and the sum over all the volumes. And so the probability is essentially the same, except we've got a new term. We've already determined the temperature by taking the derivative with respect to the energy. Now we're going to define another quantity called pressure by taking the derivative with respect to the volume. And that is the way in which we have the definition for pressure. Now, once we have pressure, temperature, and volume, we have the ideal gas law. So we've already re-derived the ideal gas law. Has anybody recognized what the log of the density of states, omega sub omega of E and VB is? Fred, do you know what the log of the density of states is?
No, I do not.
Okay. How about Lee Gale? Do you know? I guess not.
Can you hear me?
Now I can. I couldn't
Okay,
before.
I managed to unmute myself just so I could say no.
Okay, Lukowski.
I'm going to pass on this one also.
You haven't seen the headstone of Boltzmann?
I see pictures of it, yes.
Yes, this is entropy. Log of omega is K sub B times log of omega is the entropy. And we might have some problems because I just was told that my internet is unstable. All right, so the probability of every microstate is just the energy A plus pressure times volume A divided by K sub B T divided, and the exponential of that divided by Z. So this says that every microstate that has this energy, I'm sorry, I got A's and B's crossed up here. This should be A and this should be A. If you have a macro state energy E sub A and a volume, macro volume V sub A, and a pressure, which you can derive from it, or the temperature, which you can derive from it. When you have this particular expression, that is the probability of each and every microstate in the ensemble. So there's a collection of momenta and volumes for the entire space, and the probability of all of those trillions, many trillions of trillions of trillions of microstates, all are equally probable, and the probability of each and every one of those is this. Okay. Going back to our original, just the energy of the state. So the probability of the macro state is obtained by summing over all the microstates. And since each one is, anybody want, I've just said it about 3 times. Lukowski, what is it?
Must be entropy.
Well, there is the entropy in there, but these are all equal probability ones. So if you know the number of microstates, then you can, instead of summing, you can multiply by the number of microstates. So the sum goes to multiplying by the number of microstates. So Boltzmann's form, the entropy of the energy in a macrostate A is his Boltzmann's constant times the log of the number of density, the number density of microstates. And he used this rather strange postulate of equal a priori probabilities, which was in turn based on his Stochasatz, I can't do that at all, chaos assumption.
Stokes-Zahlen-Satz. Stokes-Zahlen-Satz.
Okay. Thank you. Anyway, this was he needed this in order to be able to get his H theorem, but the probabilistic view of thermodynamics, that was about 1866. 1902, the American physicist Joshua Willard Gibbs generalized the system, and in his version, he had it equal to K sub B times the probability of E sub A times the log of 1 over P E sub A. And you probably have never read Shannon's mathematical theory of communication. It's really fairly short. It's only about 100 pages or so. Well, even here we can see, but yeah, less than that. So 40, 50 pages. I mean, it's fairly straightforward. I strongly recommend that you get a copy of Shannon's and read it. It's really a beautiful paper. Anyway, the result that Shannon did about the entropy of communication gives exactly the same as Gibbs entropy, as I have shown except for the constant of proportionality, Boltzmann's constant. Otherwise, the two are identical. So we've been in the course of doing this, we've been able to use a state function. The entropy S is actually just another different kind of state function. We did originally the ideal gas, and we had the state function of pressure and temperature and pressure, volume, and temperature, and we were able to do a lot of work with that. This is a more abstract but more useful one because it allows us to use our evolution over time from states that are at different temperatures to equilibrate. And that's the reason that the more abstract state function entropy S is used, and it can be defined in terms of temperature, pressure, energy, volume, many other things. And they can all be embedded into our original ideal gas state function within the definition of entropy, which we've shown two ways you can use the definition of entropy and take particular partial derivatives, and you wind up with the ideal gas state function. So 6 years earlier than Boltzmann, Maxwell wrote a paper that defined the probability distribution of the speed of molecular motion. We talked about how in momentum space, any particular macro state corresponds to a humongous dimensional sphere in the micro state, in the ensemble of microstates. So these particular molecular motions, we assumed that the energy was constant, but Boltzmann actually derived what the kinetic energies were. In addition to this, 6 years prior to Boltzmann's H theorem, he also provided a mechanical mechanism for the tendency of a gas to equilibrate, not equilibrium, but equilibrate the temperatures of a gas. So, and that was the thing that Boltzmann was most proud of. So we're going to talk about his illustrations of the dynamical theory of gases, which was 1860. Boltzmann was 1866. And this was a real revolution basing physics on probability theory. I won't deal with all of this. It's a very large paper, but I'll describe hopefully some of the key insights and results of his computations. There were 6 sections in his publication. Propositions 1 through 3 were the analysis of particle collisions. Unfortunately, there's an assertion that he makes, which I'm calling assertion A, which is a hidden assumption in proposition 2. That assertion is starts, if a great many equal spherical particles were in motion, ... The claim is that the collisions would lead to a stable kinetic energy, that is a temperature and velocity distribution. Proposition 4 did the derivation of the velocity distribution. Proposition 5 did the derivation of the relative velocity distribution as opposed to the absolute velocity distribution, and actually in this case the speed. And proposition 6, which is the one that anticipated Boltzmann's H theorem, assumed that collisions lead to an equalization of temperatures of a mix of gases. So if you have 2 different gases at different temperatures, they will equilibrate. His assertion A in full form, if a great many equal spherical particles were in motion in perfectly elastical vessels, collisions would take place among the particles, and their velocities would be altered at every collision. So, after a certain time, the viva will be divided among the particles according to some regular law. The average number of particles whose velocity lies between certain limits being ascertainable through the velocity of each particle changes at every collision. It's a hard thing to understand. He's talking about having, and he's making an assertion that this will be the results true. He's in essence making the assumptions that he needs to make his velocity distribution turn out to be true. But he's simply asserting it, not using it as a postulate, which would have been the proper thing to do. So he's assuming that the particles are coming together and bouncing off each other, And over time, there's so many interactions that the direction which particles go off from each other will be uniformly distributed in all angles. That's what he's getting out of this. And the velocities between any two limits, that is the speeds actually, not the, he said velocity, but he's actually talking about the speed, would also be able to be inferred from this assumption. So the difference between Maxwell and Boltzmann was that Maxwell asserted assertion A. Boltzmann used it as a postulate, his equal postulate, and his, Bob, would you repeat for me how to do these stoles, however you say it?
I can't do it unless I see it written down.
Okay, I can't either. I can't even say it if it is written down, so. Anyway, Maxwell also made another assertion, which I'm calling assertion B, which he used for used both for the equilibrium of gases and for his distribution of molecular velocities. And I'll try to describe what this is to begin with. All right, so we have atoms or molecules in gases, and Maxwell treated them as little hard spheres, just as Boltzmann did, that is, little billiard balls. So now, in order to establish the energy of the macrostate of the gas, he needed to estimate the velocity of the particles. Anybody want to tell me why he needed to do that? Velocity is a vector. If the gas particle movement had spherical symmetry, which is what he was trying to get to, he could assume that all the components had identical speed. So the components of the momentum, the Vx, the Vy, and the Vz would be identical. And so when you got the energy, the kinetic energy, you would simply have 3 times the speed squared, because all of the velocities would have the same distribution. So I'm going to show you a collision here.
I have a question.
Yeah.
In a previous slide, and I believe, I'm not sure if it was the same scientist here, but what you just said about all components would have identical speed, didn't you say earlier, or someone either, I'm not sure the difference between an assertion, a postulate, and a theory, but one way or another, didn't you say that?
Well, an assertion, just to let you know, an assertion means that you're saying this is true without proof. A postulate says, I'm going to deal the system with as if this were true. So in one case, you're asserting that something is true. In the other case, you're saying, if it's true, this is the result.
Okay.
You see the difference between an assertion and a postulate?
Yes,
okay.
I do.
Good. All right, go
so
ahead.
wasn't a previous, I forgot if it was assertion or postulate, but that after innumerable collisions between the individual gas molecules or atoms or whatever, billiard balls or whatever, they will eventually all equilibrate. So
right.
Isn't that assuming, perhaps that's the wrong word, but isn't that assuming that when they started out, they were not all equal and that they had to interact in order to equilibrate?
Yes. That is absolutely true.
Okay.
But the assumption we're dealing with, remember, we're doing quasi-static systems. So at every moment, we're dealing with long enough periods of times that everything can equilibrate. That is, there can be a tremendous number of collisions so that this assumption in Boltzmann's case and assertion in Maxwell's case is true because there's been so many collisions in the period of time. So the time of period that you can measure things in macro states, that is, measure a temperature, measure an energy, etc., is so long compared to the microscopic collisions that are going on in the gas, such that you can use this either assumption or that is postulate or assertion, which Maxwell said it would be true, but he didn't prove it. And Boltzmann said, if it's true, then this is the result.
Okay, so that this second paragraph on the screen that you're showing, if a gas particle movement had spherical symmetry, then he could assume that all components had identical speed. So there's a time factor in here. It's starting at a later time after the particles have interacted for a significant period of time.
Right.
Okay.
We've been talking about quasi-static systems. We've been talking about periods of time for macro states that are very long compared to microstate behavior. So yes, all of that is absolutely accurate.
Okay.
Okay, great.
Yes, thank you.
Thank you. Okay, so now let's take a look at a collision. So here is two particles coming at each other, and they're going to eventually collide. And of course, they're not going to, they're going to be so that the surface of it is not missing. They're actually hitting a portion of it. And I think they're about to get there now. So now the energy changes from the conservation of momentum and conservation of energy, and they go off in different directions based on what the tangent of the two circles are that hit together. So, but there's another thing that I've got in here, a red dot and a ring that is also there. And so the fact that these could hit in many different places would mean you'd go off in many different directions. So you hit, you go off in a different direction than you came in, and they can be, the idea of this circle is that, well, let me go on to my, let's see, window. What do I want? Okay. Well, I may have just done something bad. We'll see. Anyway, let me share back to the slides. Where's my slides? Here we are. Okay. So there was a red ring and a red dot. The thing that I didn't say is that the collision I'm talking about here is in the center of mass frame of reference. And the red dot is the center of mass of these two particles at the point of collision. And that means that part of what's going on in the system is that that red dot is moving in some direction, but it's irrelevant to the collision itself because it's at the center of mass. The red ring is a circle around that red dot of radius, the size of the radius of the orange particle, plus the radius of the blue particle. So the sum of those two radiuses make this ring. And the reason that this was important was that assertion B was that the collision will, let's see, no, we've already said that. The impact location of the particle is distributed uniformly within that circle. That's what assertion B was in Proposition 5 of Maxwell. And this was again something that he asserted without proof, and it turns out to be almost true if you follow it closely, but it's not accurately. But it's close enough that he got away with it. And the assumption that they're all uniformly distributed around that allowed him to determine the probability distribution of particle speeds. Now we're talking about the sum of the velocities squared. So you have c squared, this is the speed squared, and here you have speed squared. And as you can see, mc squared on 2 is the kinetic energy. So the probability that he came up with for the particle speed distribution gives you, as part of it, the energy that we showed in the previous one. Now, he's assuming that this only holds between two particular speeds, C1 and C2, because when he's doing his calculations, he's dealing with assumptions where the energy is essentially always the same. So that means that the speed has to be between two speeds, C1 and C2, close enough that the energy difference is not going to be significantly different. So that was what he looked there. Now, if you actually take a look at how his distribution looks like, this is a particular probability distribution. It's the same one that he had before. The mass I've used here is the molecule of an oxygen molecule. And I'm assuming here that the temperature is 300 degrees Kelvin. And the blue is his probability distribution as a function of speed in meters per second. So somewhere between 0 and, I mean, it actually goes off to infinity, but whenever you're calculating any particular energy system, you're dealing with two systems, two speeds, C1 and C2, close enough that the difference in energy is insignificant. For any particular gas, you can get three kinds of numbers out of them. One is the maximum probability speed. So the red line that goes to the top, this is the most probable portion of the probability distribution. Wherever the derivative is 0, goes to the maximum value. That speed is the maximum probability speed. There is a mean, an average speed, and for this one is about 157. The mean is about 221 meters per second. And there's another one that you can talk about, the root mean square, which takes a look at an average over time and the bouncing that we were talking about. And this is a closely related to the mean, but time related as opposed to the overall probability version. And this one is, again, slightly larger, about 240 meters per second. So this is the kind of thing that he was trying to understand. And it turns out that this is very, very good for estimating the energy of the gas in any particular temperature for a fixed volume. Okay, so with a microstate of kinetic energy, that is a speed essentially the same C1 to less than C less than C2, we can use the Maxwell-Boltzmann distribution and Maxwell speed distribution to determine the macrostate and the entropy. And the entropy is just a state function that allows us to calculate things like probability, pressure, volume, temperature, etc. But the entropy is very useful because it allows you to do what we've experimentally determined. If you have two volumes of gas at different temperatures and let them interact, they will equilibrate. They will eventually all become the same temperature. And as I said, 6 years prior to Boltzmann, using his two assertions, he was able to show that the temperatures starting at different ones, assuming they were in quasi-static systems, that they could that each time you would go over a period of time, they'd get closer and closer and closer. And that's what we were seeing way back in our beginning 1,000 dice with 0 and 1. The same thing over time. The average of the states all went to the same value. So we were using a small model to show both the distribution over volume of the system and of the equilibration in temperature of the two. We're doing the same thing here, but this is much more precise than what I was showing as an example before. So, okay. So he established 6 years before Boltzmann that the same result that Boltzmann did. He did more than Boltzmann did because he also gave the probability distribution of the speeds. And the only problem was that he made two assertions as opposed to making them postulates. If he had just simply said, I'm assuming this to be true in both cases, he would have, you know, gotten the results to Boltzmann 6 years before he did. Pretty amazing set of results. Okay, the last idea I want to describe before we move on next lecture to information theory is Louiville's theorem. It was named after Joseph Louiville, a Frenchman. It's a key theorem in classical, statistical, and Hamiltonian mechanics. And it asserts that the phase space distribution function, that is, if you have a system interacting in Newtonian mechanics, then if you have a collection of particles within a specific initial condition, as they evolve over time, the area of all those particles will remain the same, no matter how they change. So as an example, I'm using the energy, the kinetic energy 1/2 mx prime squared minus u of x, where u of x is this polynomial in x to the 6 plus 4x3, but never can understand what that's going to be, so I draw a picture. This is the potential we're using. So using the variation, Euler's equations give us the momentum is this particular polynomial in x of t. The derivative of the momentum is that the derivative of x is the momentum. I'm using m equals 1 in this case. The mass is 1. x0 is some x0 and p0 is another x0. So I'm going to have a whole collection of points. Again, I can't deal with more than 3 dimensions, so I'm actually only going to show you stuff in 2. But the phase space, this is x and this is p. The system of initial conditions I'm using are this yellow circle. So I'm using the system for every point within that circle. And those systems will all evolve over time in this blue region. So they will move around in here, and the initial conditions of our system here have a certain area, the radius of the circle of pi r squared. So what Louiville's theorem says is that if you let that system evolve over time, this is just the initial conditions, and you let it evolve over time, it's going to evolve in this region, but the collection of points will be such that the area of those collections of points over time is going to be constant. So solving the equations, plotting the behavior over time, collecting those images into a video, and we're now going to see a different one. I closed it down. Okay, let me go off and do this. Sorry. Okay. Yeah. Okay. Is it one more earlier? Yes, it is. Okay. So Louiville's theorem. Okay. So let me stop that. Okay. Come on. There. Okay. Now I should be able to share. Where is it? All right, let's do it again. There it is. Okay. So now I can share, and hopefully everybody can see the circle of initial conditions, the region over which all of the, obviously you can see I didn't do every point, I only did a finite number of points. So there's there's a finite number of solutions going on here, but it's very close. The section here, the blue is the radius of this circle, the area of this circle, and the red is the area of what shows as it goes over time. Now, the two, obviously, you can see, will be essentially the same. They change in the fourth digit, so you can't see it in the, I mean, it is an approximation, but it's a damn good one. And in this scale, you just can't see any difference whatsoever. Okay, so you see that moves around in a really weird shape, changing over time, but the area, no matter how it moves around, the area stays constant, and that is Louiville's theorem. So we're going to keep going because this gets more and more weird as time goes on in the system, but the area continues to be to 4 significant figures the same as the initial conditions. And that is Louiville's theorem. And I'm just going to let it go. As you can see, it's getting more and more stretched as time goes on of all of those initial conditions. They get more and more entangled, but they never cross. That's another aspect of Louiville's theorem. They will never cross each other. The area stays constant, and however they distort, they will never cross each other. Those are the two main results of Louiville's theorem. So you can see there's now 1, 2, 3, 4 of them. Okay, so let me go back to, where am I? Here. Okay. So that is most of what I wanted to show you about statistical mechanics and thermodynamics. We're going to describe what we've learned so far, and then what we're going to get to in the next lecture. So I think you and I have accomplished quite a bit. We finished with our simple models of the analog of the equilibrium behavior. Then I described in detail microstates, macrostates, phase space, and the relationship to microstates and macrostates, especially energy, the density of microstates, the postulate of equal a priori probabilities, the meaning of ensembles, time averages versus ensemble averages. We talked about ergodicity and the equivalence of time average and ensemble averages. We talked about equilibrium, that is, as an unchanging probability distribution of microstates over time. The trick of separating our system into a small system and a heat bath, the assumption of weakly coupled systems, which allowed us to do the factorization of the density of states omega, the independence of the macroscopic variable other than energy, the linearity of the log of the density in energy, the definition of the entropy state function S, the definition of the inverse temperature in terms of the derivative of the state function S, extending entropy to include volume, the definition of pressure in terms of a different derivative of volume in terms of the the entropy state function. Maxwell's 1860 publication anticipating Boltzmann's H theorem, Maxwell's molecular speed probability distribution, or equivalently the kinetic energy, how Gibbs entropy generalizes it and allows unequal probabilities and matches Shannon's information entropy, and how Louiville's theorem shows that the probability distribution of a system in phase space is conserved in time. So with this background, I can finally describe Maxwell's demon, the Slizard engine, and begin to describe Shannon's information theorem. And the last lecture, hopefully, will be showing how, starting with Shannon information theory, you can get all of the results of thermodynamics or statistical mechanics before. So hopefully, any questions?
No, but there was a lot to digest there, Bob. So we'll have to all think about it. So you're planning 2 more sessions?
Right. The next one would be to talk about Maxwell's demon, the simplified version that Slizard showed, which is usually called the Slizard engine, and then doing information theory in a very simplified version, and showing how using the Slizard engine and information theory, you wind up having thermodynamics come out of the information theory. Basically, well, I'll talk about it next time. I won't go ahead.
So Bob, you're going to send out these slides, and would you do it as soon as you can?
Yes,
So
I
that
will.
while we're still thinking about it, we can go back and look at the slides.
Sure.
And
I'll be happy to do that.
even if you can post your video, that would be good. So we can go back and review some of the things you said.
Yeah, that's